Time-appropriate greetings, everyone, and welcome back. Today we're going to do two examples of two independent means, including a confidence interval and two examples of hypothesis testing. Let's get started with example 1. Asking, is there a difference in the compression strength, which I've denoted CS, measured in pounds, between cans of orange juice and cans of cola soda? We randomly sample cans of each type, 15 cans of orange juice, 15 cans of cola, each with their sample mean and sample standard deviation of compression strength. We assume that the cans are made in dedicated bottling plants, so that cans of orange juice aren't affecting the cans of cola. We have the independent groups assumption. We assume that the distributions of compression strength for both types of beverage are normal, so that we have the normal population assumption met. And we also note that the question tells us that the samples are random, so we have the independence assumption also met. Do these data provide evidence at the 5% level of significance, so alpha equals 0.05, that on average there's a difference in compression strength in cans of the two different beverage types, orange juice and cola? Let's now state the hypotheses of this problem. Given that this is a two means problem, two independent groups whose means we're comparing, the parameter of interest is going to be mu1 minus mu2, the difference in population means. We're going to assume that they're the same, or that their difference is 0, and then we want to conclude at some point if they are different, so that their difference is not equal to 0. The question didn't say whether you want to know if cola is higher or lower, so we just choose the two-tailed alternative by default. We'll define one of the parameters in context now. I'll just choose to define mu1. And mu1 is a population mean. And it's going to be the population mean of the first group, which I'm going to call orange juice. And it's the compression strength of all cans of orange juice. I'm just going to write OJ here for short. It's not a sample mean. It's not a proportion, and notice that I had to tell you what I was measuring, the compression strength, and who I was measuring it on, cans of orange juice. Let's compute the test statistic for this test. The test statistic for a test testing two means is T, which is the estimate minus the hypothesized difference, mu1 minus mu2, divided by the standard error of x bar 1 minus x bar 2. The estimate will be the difference in the sample means. Mu1 minus mu2, of course, will be 0, and the standard error we have to compute. The standard error is computed by simply taking the sum of the standard deviation squareds over the sample size and square rooting it. If you know how to do a pooled two-sample t-test, it would probably be preferable here because the standard deviations are so close. But we're going to keep this conservative and stick with the two independent, unpooled t-test. Both of the samples have sample size 15, so the denominators will be equal. The first sample had standard deviation 21, and the second sample had standard deviation 15. I plug this into my calculator and obtain 6.6633. I can now compute the test statistic. I've plugged in the sample means from the first and second sample, and I've also plugged in the standard error. Notice that mu1 minus mu2, again, is 0 because that's the null hypothesis. I plug this into my calculator and obtain negative 2.101. There's now one more piece that we need, the degree of freedom. The degree of freedom in a two-sample t-test is conservatively calculated to be the minimum of the two sample sizes minus 1. In this case, they both have sample size 15, so the degree of freedom will be 15 minus 1, or 14. Now that we have all of the pieces, we can look up the p-value. The p-value is found by looking up our test statistic on the what will be 14th row of the table T. I've pulled up table T, now let's look up our test statistic. The degrees of freedom is 14, so we'll be looking up our test statistic on the 14th row. Our test statistic is negative 2.101, and this is a two-tailed test, so we look up positive 2.101, which is in here, in between 1.761 and 2.145. We then look up to the probabilities rows to find our p-value. Since this is a two-tailed test, we use the two-tailed probabilities and find that our p-value is between 0.05 and 0.1, between 5 and 10%. With our p-value between 0.05 and 0.1, we now ask ourselves, is this evidence significant? That is, compared to our significance level of alpha 0.05, does our p-value provide significant evidence for the alternative hypothesis? We note that, though we don't know the exact p-value, we do know that it's between 5 and 10%, so that we know it's bigger than 5%. And 5% is our significance level, which means we do not reject the null hypothesis, and we do not conclude the alternative. Our evidence is not significant. Let's take this significance decision and use it to make a formal conclusion in full context. We first need to tell the readers that our assumptions are met, so that the conclusion we're about to give has a valid interpretation. And then we have to tell the reader that unfortunately, we do not have sufficient evidence to conclude the alternative hypothesis at the 5% level of significance, because our p-value is bigger than our significance level. And now we're just going to write the alternative hypothesis in full context of the problem. And that's that the population mean compression strength of all orange juice cans differs from the population mean compression strength of all cola cans. This sample does not provide enough evidence to conclude that there's a difference in compression strength between the two cans on average. Let's look at our second example. Is the stopping distance, which I'll denote by S-dist, measured in feet, of cars traveling 50 miles per hour reduced with a new braking system? That is, does it take less time to brake with the new system? I draw two random samples, 6 cars using the old braking system, 6 cars using the new braking system. I measure their sample mean and sample standard deviation stopping distance for the two samples. I assume that the stopping distances for both systems are normally distributed so that the normal population assumption is met. We also assume that the cars are being manufactured in a way that they're not interfering with each other. The two systems are not related, so that we can assume the independence group assumption. And of course, the question tells us that the two samples are randomly drawn, so that the independence assumption will be met. Do these data provide evidence at the 1% level of significance that, on average, the stopping distance for the new system is less than the stopping distance for the old system? That is the old system better than the new one? We want to know if the old system is better than the new one, so we're going to be seeing if the stopping distance for the old is less than the stopping distance for the new. And then I'm going to subtract new to get it into kind of a mu1 minus mu2 form that we're going to use in our hypotheses. Writing it like this is going to help us tell whether this is a left-tailed or a right-tailed test. Let's state the hypotheses of this test. Again, mu1 minus mu2 equals 0 is going to be our null hypothesis. We're going to assume that the two population means that we're comparing, the old braking system and the new braking system, are equal. Our alternative hypothesis is also going to include mu1 and mu2 and 0, and based on our discussion above, this is going to be a left-tailed test. mu1 will be the old, mu2 will be the new. To make that 100% concrete, I'm going to define mu1 in full context. mu1 is going to be a population mean, and it's going to be the average stopping distance of all cars with the old braking system. Like before, we're going to compute the test statistic, which is going to be a t-score. Like before, the null hypothesis tells us that mu1 minus mu2 is equal to 0, so that's going to go away. We compute the standard error in the same way as before, using the sample standard deviation and the sample sizes. And we simply plug in the values for S1 and S2, N1 and N2 into this formula and compute. Again, both of the sample sizes are the same, 6, and the sample standard deviations are 5.03 and 5.38. I plug this into my calculator and obtain 3.0068. Since this is a t-score, we're going to need a degree of freedom in order to find the p-value. Let's now use the standard error to compute the test statistic. I've replaced the two sample means from the problem, and I've replaced the standard error with that which I've just calculated. I use my calculator to find the test statistic to be negative 4.523. Since this is a t-test statistic, I need to find the degrees of freedom. The degree of freedom, again, is just the smallest sample size minus 1. Since both of the samples are the same size, this is just 6 minus 1, which is 5. Let's now use table T to find the p-value for a left-tailed test with a test statistic of t equals negative 4.523 with 5 degrees of freedom. Having turned to table T, we focus our attention on the fifth row, degrees of freedom 5. We then look for our test statistic, t equals negative 4.523. Since our test statistic is negative and this is a left-tailed test, we're going to actually just look up the positive version, positive 4.523. We notice that our test statistic is larger than the largest value. 4.523 is larger than 4.032. We look up to the probabilities row. Since this is a one-tailed test, we're going to be comparing our p-value to 0.005. Since our test statistic is larger than the largest value, that means our p-value is even smaller than the smallest value. Our p-value is less than 0.005. Given that the p-value is less than 0.005, let's now make a decision on the significance of this evidence. Since the p-value is less than 0.005, it is also less than 0.01. And since 0.01 is our significance level, we have significant evidence to reject the null hypothesis and conclude the alternative hypothesis. Let's now use this decision to make a conclusion in full context. We first tell the reader that the assumptions are met. Then we tell the reader that we can conclude the alternative. We have sufficient evidence to do so. Remember that we should always be reporting the significance level, alpha equals 0.01, and that we also should report the p-value. Now we simply write the alternative hypothesis in full context of the problem. And that's that the population mean stopping distance of all cars with the old system is less than the population mean stopping distance of all cars with the new system. That is, we probably shouldn't switch to the new system, since the old system we've been able to conclude is still better than the new one. Given that the difference between the old system and the new system was significant, let's now compute the 99% confidence interval to estimate that difference between the mean stopping distances. Let's see how much better the old one is than the new one. As usual, the confidence interval is going to be the estimate plus or minus the critical value times the standard error. Note that the estimate in this case is just the difference in the sample means. The critical value is going to be a critical t-star value, and that standard error of x bar 1 minus x bar 2, we've actually already calculated. Let's head over to the table T to get the critical t value for a sample with 5 degrees of freedom and 99% confidence. I've returned to table T where I still have the fifth row highlighted because the degrees of freedom is still 5. We're looking for 99% confidence, which is the same as a 1% two-tail probability, which is this column. This can be verified by looking at the bottom of the table and seeing this column is labeled 99% confidence. The 99% confidence column corresponds with the fifth row at our t-star value, 4.032. Back to the example, we have t-star equals 4.032. We also know that the standard error from before is 3.0068. We can now plug in the two sample means, the critical value, and the standard error to start computing this interval. I'll then compute this difference and multiply this product. I'll now subtract 12.2 from negative 13.6 and add 12.2 to negative 13.6. Our 99% confidence interval is negative 25.7 to negative 1.5. Let's interpret in full context our confidence interval. As usual, we need to tell the reader that the assumptions are met. We also need to tell them how confident we are in our results. We also need to tell them what we're comparing. In this case, it's the population mean stopping distance of all the old braking system cars being between 1.5 and 25.7 feet less than the population mean stopping distance of all cars with the new system. Notice that I knew that it was between 1.5 and 25.7 feet less than the new system because the differences were negative. When the differences are negative, the second value, the second group, in this case the new system, is bigger than the first group, in this case the old system. The old system is between 1.5 and 25.7 feet less than that of the new system.